Okay, everybody. Hi, Stuart on 3. Ready? 1, 2, 3. How about we love you, Stuart? Ready? 1, 2, 3. Okay, everybody, raise your right hand and turn to somebody next to you and repeat after me. Raise your right hand. Raise your hand. Repeat after me. I do solemnly swear that I will stay positive while we do word problems. And and if and and if I begin to feel negative, you will give me a hug. Oh wow, we totally fell apart. Okay, all right, whatever. Okay, we pick up here. Trust me, these first word problems are really not that bad. They're not that bad at all. A ball is thrown upward, with an initial velocity of 18 meters per second. The height of the ball is modeled by the equation h of t is equal to 18t minus 4.9t squared. That is the height of the ball. That's not the motion of the ball. That is the height of the ball modeled in terms of time. The question is, what is the maximum height the ball reached? Well, that's an interesting question. Let's think about it for a second here. When it reaches its maximum height, what is the velocity? 0. Why? The velocity changes from positive to negative. And if you think on the number line, if you move from positive to negative, you have to cross over 0. And so it's motionless at that point. So we want to figure out where the velocity is equal to 0. So first, let's find the velocity. Velocity of t is equal to what? Bryce, you're a genius. How did you get that? You took the derivative. Just derive it, baby, right? When in doubt, take the derivative. When in doubt, take the derivative. Derivatives identify the rate of change, and we are wondering when the rate of change is exactly 0. So we take the derivative, and Brady said that the derivative is equal to 0. The rate of change, the velocity, is equal to 0 when it changes direction. So we will say 0 is equal to 18 minus 9.8t. If we solve for that, 9.8t is equal to 18. Divide by 9.8. And what we get is, Stuart even sees my calculator, which is really cool, I think. 18 divided by 9.8. 1.84. We'll round to the nearest hundredth. Time is equal to 1.84. 1.84 what? Seconds. No, I have two functions. I have a position function. This is the position function. I also have a velocity function. That's right here. They tell me two different things. Question B says, what is the height of the ball? Question. What? Oh, okay, good. Yeah, excellent, excellent. Okay, you caught me. Stuart, Morgan asked a great question. She said, we found the time, but what about the height? I'm sorry, I did not answer the question. The question says, what is the maximum height? So once I have the time, where do I plug it back into to get the height? The original, the position function. The position function actually tells me up and down where I am. So now I will go h of 1.84 is equal to 18 times 1.84 minus 4.9 times 1.84 quantity squared. Does somebody have that result? 16.53? 16.53? Okay. So 16.53 meters would be the maximum height, and it reaches it at a time of 1.84 seconds. Everybody clear on that? That is a foundational thing that we will continually move towards in calculus, and the fact that you guys got that is excellent. Now the question is, what is the height of the ball after 2 seconds? Which one do I use? The first one. Very good. H of t, or h of 2, is equal to 18 times 2 minus 4.9 times 2 squared. 18 times 2 minus parentheses 4.9 times parentheses 2 squared. 16.4. So after 2 seconds is at 16.4. What is the velocity after 2 seconds? How about this? Can you tell me, should the velocity be positive or negative after 2 seconds? Why? Because it already reached its maximum height. It's on its way back down, so it should be negative. So I plug it into the derivative, which is the velocity function. V of 2 is equal to 18 minus 9.8 times 2. Negative 1.6. Negative 1.6 what? Meters per second. Bryce says it is a derivative, thus it is a rate of change, so we must have a rate. Something per something. That'll be the definition of the derivative. Again, rate of change. How you doing so far? Good. All right. Everybody's staying positive. No hugs needed. Very intuitive of you, Dr. Shodi. Yes. Okay, at what time does the ball have a height of 20 meters? Uh-oh, now what? First equation or second equation? First equation, height of the ball, when is it 20? So 20 equals the height of the ball, 18t minus 4.9t squared. So, okay, we'll get to Claire's question. Claire, what is your question? Very good. So since the maximum is 16, we shouldn't be able to solve this, correct? So let's suppose, though, that we need to show that it doesn't reach that height. If we were to solve this equation, what would you use? The quadratic formula. We won't carry it all out, but watch what happens, because this will help you as you do your other problems. 4.9t squared minus 18t plus 20 is equal to 0. I brought everything over to one side. The quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. So negative b would be 18 plus or minus the square root of b squared, which is 324, minus 4 times 4.9 times 20 all over 2a, so 9.8. Watch. And then you will understand. You will say, oh, I get it. Minus 4 times 4.9 times 20. Negative 68, what does that mean? Why? Can't take the square root of a negative. You would get an imaginary solution. So that means that there is no point where this equation is solved. So it does not reach a height of 20. Because we get a negative solution underneath the square root sign, therefore, doesn't reach that height. But if it did, then you would have those two answers. Okay? Yeah? Well, the question is, at what time. So we would probably get one time for the ball on its way up and another time for the ball on its way down. Good? Okay. Couple more problems. Neither one as long as that. Boyle's law. Boyle's law states that when a sample of gas is compressed at a constant temperature, the product of the pressure and the volume remains constant, namely that P times V is equal to C. Do you guys know that? Okay, you learned that in chemistry, I'm assuming? Okay. Ooh. Whoa, struck a nerve there. Okay. we won't go there. All right, I did not hear. So rate of change of the volume with respect to pressure. Okay. Now let me just make sure we understand this. Okay. It's saying the rate of change of volume. So what we want to find is we want to find V prime. With respect to pressure, that means that pressure is our variable. How can I rewrite PV equals C so that it's written as a function of volume with pressure as the variable? How would I do that? Very good. So pressure is equal to a constant, which is just some number, say 4 or -3 or whatever, divided by, well, I'm sorry. Sorry. Volume is equal to the constant divided by the pressure. That's what you wanted. So we're writing it in terms of the volume. Pressure is our variable. And it says find the rate of change of that. So I want to find V prime. So I want to take the derivative of that. Well, this is just a number, and this is a variable. So it would be something similar to say, well, I don't know, 3 over x. If you were to take the derivative of that, not 0, watch what we'll do. V is equal to C times P to the -1, correct? So that means that V prime is equal to, what do I do with the -1? Drop it in front, so -C times P to the -2. Or V prime is equal to -C over P squared. Well, you know, that's okay. That's okay. You know, there's as I think back, there's a number of problems I never would have got on my first try. That you would have to see an example first, without a doubt. That's how education works. So don't feel bad if you wouldn't have gotten that on your first try. You've seen the example, and you're gonna have a problem in your notes or your homework about that, and you can get that. Actually, it's the same exact problem. So, just a little bit different here. It says a sample of gas is in a container at low pressure and is steadily compressed at a constant temperature for 20 minutes. Is the volume decreasing more rapidly at the beginning or the end of the 20-minute period? So what happens here is we have this stuff, and we start this timeline from 0 to 20 minutes. We're compressing it. Well, let's think about it. I don't know how this works. I'm not necessarily a science guy, but what do you think is going to be happening if we're compressing it? Do you think the volume is going to get smaller more quickly right away, or when it gets all the way up to 20? Like, let's say you compress something. What's something you compress? Okay. What's something you physically compress in your hands? Like springs. Okay, so like, let's say when you're compressing a spring, is it easier to compress it, you know, for the first half or the last half? The last half, there's more resistance, isn't there? So maybe that's what's happening. I don't know for sure, but let's figure it out. The question is the volume decreasing more rapidly? So that's a rate at the beginning or the end. So all I want to really find is, you know, V prime of 0 and V prime of 20. So we have V prime of 0. If we plug in 0, we would get what? Into the derivative. You can't really plug 0 in for P, can you? So let's try to plug it in after, say, 1 minute. Let's try to plug it in, say, 1 minute. What are you going to get? Negative C? Yeah, I'm sorry. You can't really plug in 0, so let's plug in 1, and we would get negative C divided by 1 squared, which is negative C. So it says at the beginning, so around that beginning time. So we'll just see it 1 minute, and then we'll check towards the end. Well, if we check towards the end and we do V prime of 20, we get negative C over 20 squared, which is negative C over 400. So which one's more negative, the first one or the second one? The first one. This one is going to make it closer to 0 because you're dividing by that 400. So it looks like it's decreasing more rapidly right at the beginning. Just like Luke said, when you take a spring, compressing at the beginning is easier, and it's going to compress more quickly compared to the end. Okay, so same type of thought. So I have a problem that models very similarly like that in your notes or in your assignment. It's just I just changed one of the numbers. And then let's go to the last one, and then you guys can have some time to work on this here, okay? Okay, the last example I want to get to is an example of economics. And this was new to me. I've seen most everything when it comes to calculus textbooks. I would say, maybe, 90% of it or 95% of it is stuff that I know. But every once in a while I come across something where it's like I haven't seen that before. And I didn't see this example before. But this is good stuff. This is helpful stuff. So the cost function is the cost of producing X number of items. So in this example, I say a company produces X number of shoes. The cost function can be determined by this. C of X is that. Well, then we want the marginal cost function. And what the marginal cost function is this, C prime of X. And the reason why we say marginal is it really tells us basically approximately the cost of producing, I'm so popular, the next item. So, for example, if I'm making shoes, okay, is it going to be more expensive to make the first 10 to get going, or more expensive to make, say, the 500th, 500 first, 500 second? The first few is going to be more expensive, okay, just for the sake of time and everything you have set up. So this derivative tells us the cost of producing that next item approximately, how much it would go up by. So here's what we can do. It says a company is producing X number of shoes. The cost can be estimated by the following function. C of X is equal to 10,000 plus 5X plus 0.01 X squared, where X is the number of shoes that we're producing. The question is, what is the marginal cost function? The marginal cost function is the derivative. We always take the derivative. So C prime of X is equal to, what is the derivative of that? Five plus 0.02x. The derivative of 10,000 is 0. Derivative of 5x is 5. And the derivative of that, we again drop the exponent down and multiply. So that's the cost. Or I'm sorry, that's the marginal cost function. So that's about how much it costs to make each extra one. So it says, what is C prime of 500? We would simply plug in 500. So 0.02 times 500 is 10 plus 5 is 15. So we have C prime of 500 is equal to 15. The question is interpret what C prime of 500 means. What does that mean? When producing the 500th shoe, the cost to produce the next item is 15. So the rate of change. So it looks like to produce the next one. So think of your look at the slope up there, okay? It's going on to the next one. Okay, the line is going on kind of to the next piece. If we were to look really closely at that function, we're moving right on to the next part of the graph. It should be really close if we zoom in, and that's the idea. We're moving on to that next piece. So what this truly means is the rate of change of 500 is 15, which means the rate of the cost of producing the 500th shoe is $15. Sure, we could say 500 first. We could say 500 first. Yep. We could say 500 first. That'll be fine. They're really close together, okay? So we're going to get to exactly your point right here. And it says compare C prime of 500 with the cost of producing the 500 first item, okay? Well, so here's what I want to do. I will actually find out that change. What is the cost of 500 and what is the cost of 501? And hopefully that change, that increment, should be really close to 15. So what I'm going to do is I'm actually going to go straight to my calculator. I'm going to go to y equals, and I'm going to type it in. 10,000 plus 5x plus 0.01 x squared. And so I have this cost function right there. And if I go to my table and I say, what is the cost of producing number 500? It's 15,000. What's the cost of producing 501? It's 15,015. I'm getting your question right now. You asked the next question. Cost of producing 500 items is $15,000. Cost of producing the 500 first item is approximately $15,015. What was the change? 15. So you know, it says, okay, so Sammy's question, she says it's looking for C prime. Compare C prime of 500. C prime of 500 was 15.1, right? Or 15 point, oh, it was 15. So C prime of 500 was 15. Did the change go up by 15? Yeah, it did. So what we're saying is that the increase for the next item was really close to what we had. Question. The rate. So if we found the rate, so if we're going to produce more items, it's going to cost more no matter what, right? However, the rate is going to decrease. So for example, to produce the first and second shoe might have been like 30 or 40 bucks a piece. And then to produce the 100 shoe might have been more like, well, now it's only going to cost us an extra $20 a piece. And by the time we get up to 500, well, now it's only cost us $15 a piece. So the more we produce, the more we save on time and everything else, and we think that rate is going to decrease, which would be the second derivative, which we haven't gotten to yet. Yes. No, no, exactly. If we checked between the 100 and 101, we wouldn't see 15. We would see a bigger number than 15 because it is not as cost effective to produce just 100 as compared to 500. Does that make sense? Excellent questions. Great job. Everybody say goodbye. Stuart on 3. 1, 2, 3. Wake up. Oh no. Ashley got bored. Bye.